Well, greetings, everybody. Greg Freeby with the American Segmental Bridge Institute, and welcome to the June webinar. Hopefully you all are able to get logged in and hear the audio and see the screen fine. I'm going to go ahead and show some slides to kind of familiarize you with how the webinar will go here today, and then I will turn it over to our presenters. Again, I'm Greg Freeby at the American Segmental Bridge Institute. Encourage you, if you're not already following us on LinkedIn, I'd encourage you to do that. Just search American Segmental Bridge Institute and follow us on LinkedIn, and you're welcome to follow me as well. You'll see sometimes different content between what I'm posting and what ASBI is posting. So quick announcements. I want to make you aware of our next webinar, which is in June. It's the last Wednesday in June. We're doing all of our webinars on the last Wednesday of each month. So June is lined up. We're going to be talking about the use of flexible fillers on the project, the Wekiva project there in Florida. Rob Bennett from RS&H and Garrett Jones from Superior Construction are going to be joining us for that presentation. So I encourage you, that's already up on the website. You can register for it now. It's underneath the events tab on our webpage. Another event we have coming up is our 2021 convention and committee meetings. You can see on screen the kind of the schedule for when the committee meetings are prior to convention, and then the convention will actually begin at 1 o'clock on November 8th. That's a Monday. We'll have our kickoff. Our convention will run through Monday afternoon, all day Wednesday, and then Monday morning, or I'm sorry, Wednesday morning. Then is we'll wrap up about noon. We're working on our technical program. I can tell you it's going to be jam-packed. I think we had about 3 times as many submissions for topics as we have space for. So it's going to be definitely the best of the best, and maybe some of it will become future webinar content as well. So with that, let me run through sort of some instructions for the webinar today. If you lose your connection, that's fine. You can just rejoin with the link you have. You will miss content while you're away. We will be monitoring attendance time to ensure that kind of the minimum attendance time was met for attendees to be issued their certificates for completion. With regard to the certificates, please allow 1 week to get your attendance certificate by email. If a week rolls by and you haven't heard from us, then certainly pop me an email and let me know, but you should be getting your certificates for attendance next week. So we're going to do question and answer at the end of the presentation, and I'll kind of walk through what that's going to look like. So if you're on a desktop, you should have a little a little pull down dialog on the control panel that says questions. And if you just click on that, then there's a place where it says enter your question here. You can type into that dialog box. We'll hang on to all of the questions and then be answering those at the end of the session. If you're on a mobile device, you should have a little question mark in the upper right-hand corner, kind of same deal. Just click on that and you'll be able to type in a question. Mr. Tim Berry with RS&H will serve as our moderator for the Q&A at the end. We may run a little long on Q&A. If you have something else, a conflicting appointment, you can't make it, that's fine. Any of that content we do after the top of the next hour won't count, I'll say, against you in terms of your minimum attendance for a professional development certificate. We just want to answer as many questions as we can, and so we've been running just a little bit long on our sessions. So with that, I'm going to introduce our 2 speakers. We have 2 speakers today. The first speaker will be Kimberly Coleman. She's an engineering manager with the New Mexico DOT Bridge Bureau. She has over 12 years experience in bridge design, load rating, and construction. Her first 5 years of her career, she was at Parsons Brinkerhoff. She's been at the New Mexico DOT since that time. She holds both a bachelor's in civil engineering and a master's in engineering management from New Mexico Institute of Mining and Technology, as well as a master's in civil engineering from the University of Illinois Urbana-Champaign. So For the Canadian River Bridge project, Kim served as the Bridge Bureau representative and provided consultant oversight from final design through construction. Then our second speaker today will be Nyssa Beach. Nyssa is a structural engineer and project manager for Jacobs with over 13 years of experience, a graduate of Virginia Tech University. She lives in Denver. She's been involved with the US54 Canadian River Bridge project team throughout preliminary design, final design, and leading Jacobs design support during construction. So she's been involved from the very beginning of the project. So with that, I'm going to turn over the presentation. Nyssa is going to serve as our presenter, but Kim Coleman is going to be doing the first part of the presentation. So.
Are you able to see my screen yet? Oh, I think you're
We're seeing your desktop. Sorry.
Okay. So can you see the presentation now?
Yes, we can, and you're in sorter mode. So if you just start the presentation, then you'll be good to go.
All right.
All right.
Oh.
Oh yeah, you don't want to be in presenter mode. It is, where is that?
All right.
There it
should
is.
Be coming up. There we go. All right, Kim, if you want to kick it off, it looks like we're good to go now.
Ready to go. Thank you, Nyssa. Okay, so we're here to present to you the project as it currently stands, US54 over the Canadian River Bridge replacement. So this is our existing truss right now that you see on the first slide. I think you all have dutifully memorized this slide already, so. Okay, so as Greg was saying, I'm Kim Coleman. I oversaw the final design and construction phase of this project for New Mexico DOT. And I'm pleased to be presenting today with Nyssa Beach from Jacobs Engineering. We've been working closely together, very closely together for the last couple of years on this project. So just to give you an overview of this project, you can see on the right side the existing truss, and then on the left side of the picture the new bridge. So you can see how much wider the new bridge is than the old, and it was very much needed to have this extra width for all of the trucking activity that happens on this corridor. I also want to point out while we're here, right in the middle of the picture, you can see a temporary access bridge that the contractor was able to use during construction. And this saved them from having to drive out of the project and across the existing truss to the other end, because they could not obviously cross the river any other way. And our environmental folks worked very hard with the contractor to site this bridge at the narrowest location they could to avoid disturbing the wetlands. So if we go on to the next picture, you can see the bridge almost entirely complete. Right now, we're putting an epoxy concrete overlay on the bridge, and we're hoping that this really helps with sealing up the segment joints and making sure that we limit water intrusion into the inside of the bridge for as long as we possibly can. So you can see that dark overlay on the bridge right now, and then the Canadian River Truss in the background. I do want to point out the town of Logan at the top of this picture. That is the entire town. So you can completely run around the town in under an hour. I think it has less than 1,000 residents. So Nyssa will talk a little bit later about some of the challenges the contractor faced with hiring local skilled labor to assist with the construction. Okay, so here is a video just to give you some orientation to the site. If you weren't looking carefully, you missed it, and span 1 formwork was set up. Now we are looking at Pier 1 cantilever, and you can see that the form travelers are up. And I think that the left one here is launched and ready to pour. And then you can see this method of construction was really helpful in keeping us out of the river and the nearby wetlands. So the contractor has fencing around the wetlands to keep out of it, and they were very careful with not dropping anything or washing anything into the river. This is Pier 2, and you can see that they've got most of Pier 2 table built, and they're getting rebar set into the top deck on Pier Table 2. This is an access road that they were able to grade down the slope from abutment 2 so that they were able to drive across the river up that slope and work on abutment 2. And then here is end span 2 already poured and just waiting for cantilever 2 to be built up to it. So I think that's close to the end of the video. Here we circle around again. Okay, so let's familiarize you with this site. Most of you know where New Mexico is, I'm sure, but you may not know that the main north-south road going through Albuquerque is I-25, and the main east-west road through Albuquerque is I-40. So Logan is on the far east side of the state, about 30 miles north of I-40. And this happens to be, as you can see up in the right-hand corner of the town, mascot is the Longhorns, the school mascot. And it's also predominantly rural ranching kind of community, but they have recreational use from the nearby Ute Lake Reservoir. Okay, so why we need this project? The existing steel truss was built in 1954 and rehabbed in 1984. So it's been over 30 years since we've done work on it. It's got the typical truss deterioration, pack rust, rusted and distorted bearings. The joints are starting to fall apart. We also have some concerning cracks in the substructure, and most of you know, I'm sure, once you start to get deterioration in the substructure, you really got to be working towards replacement. It's also quite narrow, as you saw from the first photo, and has fracture critical connections, as we all know from trusses. This existing bridge has a 120,000 pound load limit that our bridge management team has set on it. What you see in the picture right here is actually an emergency inspection that we had to conduct during construction of the new bridge because an overload got lost and drove across the bridge during one of the nights, and his axle weight was 240,000 pounds. And again, unfortunately, he realized he was lost after he crossed over the truss, and so he turned around and came back. So 2 times this overload crossed over the bridge, and so we were out there looking at all of the connections, making sure we hadn't lost any rivets or seen any unfortunate distortion because of that. So it can be exciting construction sometimes. Okay, to discuss project need, half of the traffic on this corridor is trucks. And that's because it's the main corridor from El Paso to Chicago. So you can imagine if this corridor were shut down for any length of time, the kind of supply train backup that would cause. I-40 also has some width and height restrictions that US54 does not. So it was really important that we have this connection over the Canadian River able to accommodate oversized and overweight loads and allow for that commercial traffic. The corridor is also very important to the village of Logan, and I'll talk about that in just a little bit. But we had to replace the bridge to address the existing deficiencies with the truss, make sure we could accommodate the oversized and overweight loading, and make sure that it would last a long time into the future. So go ahead now. Okay. The upper left map, you can see again the village of Logan kind of up and in the middle on the map. One of the chief concerns of the village is that that corridor provides most of their business. I think that every restaurant and motel in the village is along US 54. So if we had realigned US 54 going through the village, or if we had closed it for any amount of time to build the new bridge, the village would have suffered greatly. So we couldn't do that. and that drove much of the final alignment. A couple of other things we had to consider with the alignment were a cultural site, wetland mitigation. We were trying to minimize wetland mitigation. And we also had a geologic seep that we had to consider when siting the foundations on the new bridge. So we can go ahead to the next slide. This is just a closer look at the alignment across the river, and the village of Logan is up to the top of the picture and towards the right. Because of the wetlands, because of the environmentally sensitive river, and because of the village location, this is the alignment we chose, which allowed the bridge to be built entirely before we took down the old bridge. So all of the traffic could continue through Logan, and the main span of this bridge could go completely across the river so we could avoid disturbance to the environmentally sensitive river and wetlands. Now, here are the two most important species in the entire project. These two fish are both state listed, and one of them is also federally listed. And if you look at some of the biological maps of where these occur, they really are limited, and the Canadian River is one of their main habitats. So we had to be very careful to avoid the river, to avoid spilling into the river or washing out into the river, so that these two guys could just continue to live and observe the bridge happily without being affected. We also had to be very careful to avoid the wetlands. So that is one of the driving factors that set our main span length. And it was also one of the driving factors that set the type of bridge, because we needed to be able to construct it without mucking around in the river and wetlands. So the next slide is just a quick touch on the various types of structures that were considered and how we finally landed upon a cast-in-place segmental. Its efficiency for long spans and ability to accommodate a horizontal curve were two of the main ones. That it could be constructed from above without touching the river was another one. It also ended up being a lower cost than the other alternatives. And we are looking forward to a long life with this bridge with very little maintenance. So hopefully we'll see that as it ages. And it also is just a really nice looking bridge that fits in with the landscape now. So I will turn it over now to Nyssa, who will take you through the design and construction.
Thanks, Kim. So I'm going to run it through some of the background and overview of our design and construction support for the project. So what you're seeing here is a portion of our 3D model that we use to do the design of the structure. Here's another view of that. We used Midas Civil 3D for the final design of the structure. And something interesting to note is that McNary Bergeron provided the construction engineering support. They used BD2 for their longitudinal construction analysis. So we had a really great comparison during construction of all of our construction load cases and our construction analysis, working with McNary Bergeron from what we had looked at with our Midas model. And this was really valuable for any changes that occurred in the field, any contractor initiated changes. McNary Bergeron would provide their review of it, and we were able to follow along with updating our Midas model to validate results and provide any input along the way. So a couple of notes with our Midas 3D model. Some of the pros with using Midas is that it is a great resource for accommodating the stage construction modeling that we needed to analyze during construction and make sure that we were getting in all those locked-in stresses that is unique to the segmental construction. We were also able to input the variable geometry of the structure, our horizontal curve, our variable depth, and our unique post-tensioning layout with the structure very easily with Midas as well. Some challenges that we had using the program, the load rating module was a challenge. We ended up having to pull out all of our loading and do the load rating analysis separately outside of Midas. And part of that was because initially it didn't incorporate the stage construction loading into the load rating analysis. It would only pull in static loading, which kind of defeated the purpose of what we were looking at with our structure. They had since fixed that. And another issue that we had found is, you can see here on the side, Midas uses a Caltrans equation for the pre-stressed concrete bridge load rating, and this includes the subtraction of adjacent vehicle in the load rating equation, which creates a more conservative load rating results than we're actually looking for. So just some things that we had to be aware of, kind of digging into the program. Another challenge that we came across was that Midas they envelope their loading, their live loading, into min and max cases, which is really helpful for the superstructure, but is not necessarily the most conservative case when you carry it down to the substructure loading. We're really looking for the concurrent reactions to create the worst case scenarios on our columns. So that was something that we had to go through more manually in Midas to make sure we were capturing that loading. Here's just some overviews of our overall geometry. So our span layout, we have 3-span structure, 2 end spans that are around 200 feet, and then our main span, 325 feet, which spans the Canadian River, the wetlands, and long-term flood levels, 100-year flood levels. We were completely out of all that with our pier column placement. Here's a quick view at our bridge section. We had a variable depth, which varied from 18 feet at its deepest at the piers, and then shallowed up to 8 feet at mid-span and end-span. And you can see we have a 43-foot wide section that accommodates lanes in both directions, as well as an 8-foot shoulder in both directions. And this is a quick view of our bulkhead, showing the post-tensioning duct layout here. And we had, for our longitudinal post-tensioning, we had 16-strand tendons, but we had an anchorage system that could accommodate 19-strand tendons. And this allowed for some flexibility to accommodate anything that came up in the field that we could take into account some extra tendons if we needed to. And this did come into play with a field design change that I'll touch on a little later. So just to run through our construction sequence, the first thing we have is that the pier tables are built, pier table 1, pier table 2, and they're built half a segment out of balance in one direction, which you can see here. And this allows us during cantilever construction to only ever be half of a segment out of balance versus a full segment, and help mitigate those out of balance loads that are carried down to our substructure. Following the construction of the pier table, the form traveler is placed, and the first segment is able to be built. The contractor did make a field design change here to extend our pier table in order to be able to place 2 form travelers on the pier table from the get-go, which I believe saved them construction time, about a month of construction time or so, to be able to do that. Once we have both form travelers out there, we're casting segments back and forth in either direction. So we cast the first segment, and then we post-tension the corresponding tendon, longitudinal tendon, across the top. Then the next segment is cast, and it's tensioned across the top, and the form traveler advances out. It goes back and forth in balanced cantilever, back and forth, until we have a full cantilever built out. for cantilever 1. And then the same process is continued on cantilever 2. It is cast back and forth in balanced cantilever construction until we have a full second cantilever that's built out. So for design, we had assumed a closure sequence of span 2 being closed first, using the form traveler to do this, followed by span 3, and then span 2, span 1, and then span 3. So for design, we were going 2, 1, 3. This was a field design change. The contractor opted to change the closure sequence to span 3, followed by span 2, and then span 1. And the purpose of this was in order to be able to remove the form travelers sooner and use closure beams to conduct the closures instead. Doing this added some additional stress to our center span, but this was something that we were able to easily accommodate with our additional strands for our continuity tendons, because we had the capacity, like I had mentioned before, to add some additional strands to those during construction. Following this, our bridge rail is placed, and our overlay, which is being placed now, is placed. Jacobs provided construction engineering support, so this was something that I was heavily involved with during the project. So I'm going to go through a couple of items that we went through to support the construction engineering. This included creating a comprehensive concrete repair plan, providing post-tensioning and grouting support, geometry control, quality assurance, and then top of deck LiDAR scan and heat map that we had done most recently with the review of the overlay that was going to be placed. And here, just I have a picture to show. I think that when you work on a project from preliminary to final design to construction, it becomes a little bit of part of your family too. So my daughter created her own concrete repair plan during construction, when she knew that we were working on some concrete repairs. And in this picture, she recommended that in areas where there's concrete cracking that you can see here, that you address it by building up some brick towers, because she knew that bricks were really strong from the Three Little Pigs, to address that. So just a little side note on how it seeps into the work-life balance. So for the comprehensive concrete repair plan, this was really valuable during construction, because we were able to get a repair plan that identified both approved products for repair as well as the acceptable limits for on-site repair without a further submittal or engineering review. And this helped the folks in the field to be able to quickly address items that came up without having to go through the entire submittal process and getting an additional engineering review, and it be very clear what was acceptable to be repaired on site. For some more significant repairs that came up, and we have a picture here showing the interior of one of our segments that had some concrete consolidation issues, and we needed to, in addition to the repair, validate that we had solid concrete throughout our section here. We worked with the contractor to perform non-destructive testing, and this was some impact echo testing. So you can see that there's a grid that's laid out on the concrete face. The non-destructive testing team performed impact echo and were able to identify areas that potentially had poor condition that we could go back and analyze and make sure were addressed. And so we were able, for more significant repairs, we were able to go this route, but the concrete repair plan, we were able to address anything that was quick and easy on site. Another support that we provided during construction was review of the post-tensioning and grouting along the way. You can see here, this is a chart showing our tendon elongations for our longitudinal tendons for each segment. And so as our segments are cast out, our tendons get longer, and we were able to follow a trend that showed that our elongations were decreasing as we extended the length of our tendons. And with this, with elongations that were shorter than theoretical, we worked with the contractor as we noticed this trend to come up with a flow chart that allowed for addressing these shorter elongations in the field without having to go back and do a significant engineering review on it. And here's just a picture of the longitudinal tendon stressing. So these were just some items to help keep things as efficient as possible in the field. Geometry control QA was another important item during the cantilever construction. McNary Bergeron performed the geometry control, and we worked with them by providing the QA on this, as well as the geometry control survey QA. So as McNary Bergeron and Malcolm were out there surveying and figuring out how they were going to aim the form travelers to not only just meet theoretical, but also aim for the as-built conditions of the adjacent cantilever and the inspans to meet. Our team was reviewing this and following along and working with them to collaborate on it during each step of the way. And here you can see a view of our entire tendons prior to closure. We had a very successful geometry control. Our final closures were within half an inch of each other for our vertical, and even tighter for our horizontal geometry. And this is just a quick slide showing the horizontal geometry control. We did have the horizontal curve of our alignment, and so we followed along throughout, checking our as-built conditions for each segment. Each of these colors represent a different segment compared to theoretical and where we're aiming along the way. And so we were closely following these at each stage to see where we were and where we needed to be. And this communication and collaboration went really well for the geometry control during the project. So a neat additional item that we worked with New Mexico DOT on was following cantilever construction, or following the cantilever construction and the closures. The geometry control, aiming up and down, led to us having some high and low spots on our deck in the end that needed to be addressed. And a lot of times for segmental construction, you'll have a thicker overlay, 3 inches or so, that you can just kind of lay on and even out your finished surface. But for our structure, we have a 3/4 inch polyester concrete overlay that is very expensive. Kim, I think it's like $43 a cubic yard or so. So we wanted to make sure that we were minimizing any additional overlay placement as best we could. And this is where a LiDAR scan and coordination really came in handy. So I'm going to play this video, and it might be a little choppy, but yeah, okay. So our LiDAR team came out and did a scan of the finished surface, and they created a digital finished surface of the scan that we compared to a theoretical finished surface, and that is how we created this heat map. The heat map identifies the areas that are green where we're matching up very closely with our theoretical. The areas that are blue are where we are low, and then the areas that are red are where we are high. And we put a grid of our segment joints on there because those are easily identified in the field. And this allowed the field crew to come in and do some very precise pinpoint deck grinding that allowed the overlay placement to be put down very, very effectively and not have additional resources or materials with that costly overlay. So a couple of challenges, Kim kind of touched on this a little bit, a couple of challenges for our project compared to other projects, with this being a very rural environment. The first one is the local workforce. So Malcolm International, they did the segmental construction. They brought in some crew from California where they're located for the supervisory personnel, but they still needed to pull in a lot of local workforce for their crew on site. And so this was a challenge on site, and they addressed this by creating some unique training resources for the construction crew to get them up to speed on a unique segmental construction method like this. The picture you see here at the bottom is a rebar mock-up that Malcolm did on the ground before the crew was setting up the rebar up in the air, and this allowed the crew to get some practice with setting up the segments, and also to do some practice with items that would prove to be difficult, including our variable depth web bars, and this allowed us to identify some efficiencies that we could come up with the construction crews, such as splicing these web bars in the field to allow for some quick placement. And then they also created these SketchUp models of the form traveler to be able to train the crew on form travelers and just the nomenclature of all the different segmental specific equipment on site. Another challenge that was unique to New Mexico, I at first thought New Mexico probably comes off as a hot desert environment, but a unique part of this area is the weather changes. So this shows the change between just 24 hours, going from hot weather to snowy in New Mexico. It can change very drastically. And this was a challenge with both the materials and the construction planning and the operations on site. So the closest ready-mix concrete supplier was 30 miles away in Tucumcari, New Mexico. And this is Pacheco Construction, and they're a small family-run business. They had never undertaken anything as significant as this project in the past. So another way that the contractor had met the challenges of this with the rural location is they helped bring the concrete supplier up to speed. I know that they helped get them some more advanced equipment and capabilities. They also moved they relocated the batch plant on site right there in Logan. So this helped to ensure that we didn't have any issues with trucking in concrete from 30 miles away. that it was able to be addressed right there on site. I'm just going to run through some of the construction photos to give you an overview of how construction went. So here you can see the forms around our twin wall columns being placed, and the bottom of pier table 2. Also in span 1 is being placed right here. And you can, this is a good picture for showing the limits of the wetland and that fencing that's around it and what needed to be completely untouched and avoided during the construction. Here's the placement of the form travelers on pier table 1. And you can see it's built out, half a segment out of balance, and the contractor is getting both of those form travelers up there from the get-go. And it was a tight squeeze up there, but the form travelers just fit, and this was able to help really kind of speed up the construction time. Here you can see cantilever 1 advancing out and completely spanning our river and wetlands. Again, this is cantilever 1 advancing out, getting closer towards inspan 1. And while cantilever 1 is being constructed, pier table 2 is being constructed on the other side, as well as inspan 3. Following the full cantilever construction of cantilever 1, then cantilever 2 had its turn with the form travelers going back and forth on either side. And here is cantilever 2 being constructed, and we are getting very close to closure here at span 3 and span 2. You can see our transverse post-tensioning. We had transverse post-tensioning along the length of the bridge as well. And a view from below, this shows has a good view of cantilever 2 being constructed, and also just that variable depth and the horizontal curve of the structure. As I mentioned before, the contractor opted to use closure beams to get the form travelers off and be able to save some time and money with the cost of having those form travelers on site. So they use the closure beams to perform the closure. This is the closure at span 2, and we were within ½ an inch of our final geometry, which was really valuable in that we were able to avoid any additional locked-in stresses that would come from correcting misalignment. And here is a good view. You could still see those closure beams in the middle of span 2, but here's a good view of our cantilever construction just about completed. And here's the completed structure. I'm going to kick it back over to you, Kim, to take over some of these last slides.
Okay, thanks, Nyssa. So this slide is just intended to show you kind of the size of the team that we were working with. So design was just the 3 agencies, and MDOT, Jacobs, and Federal Highway. But once we got into construction, we had Jacobs as NMDOT's construction services engineer. NMDOT and FHWA were providing project oversight. Fisher Sand and Gravel was the prime contractor, and they did most of the roadway and the grading work. Malcolm was the bridge subcontractor, and then, as Nyssa was talking about earlier, McNary Bergeron was serving as Malcolm's engineer. So you can see the size of that construction team and all the people that were involved with each group that needed to be working together throughout construction. So you can imagine that each submittal needed to be touched by a large number of people. So what we have here at the top is the official line of communications for submittals, and they need to go linearly through each of those entities and then all the way back. But as most of you know, on segmental bridge construction, you have some really time-sensitive things going on, especially with the segment casting. So what we allowed to happen during some of these time-critical and collaboration-dependent activities was that Jacobs and McNary Bergeron were able to communicate directly and just keep us copied on all of the communication. This happened especially on post-tensioning and grouting submittals and the geometry control items. We allowed kind of like a advanced submittal, so they could just send the technical data along, which would allow Jacobs to get started on the review while Malcolm and McNary Bergeron were preparing and collating the official submittal to come through. So we still did end up going through this official linear process, but we shortened the amount of time it took at the end for review by having some advanced technical data available. Another time that we needed to do this was when the contractor submitted a field design change to raise the pier foundations. There was a great deal of load discussion going back and forth between Jacobs and McNary Bergeron, and it really needed to be a verbal discussion, and so we needed to be able to have Nyssa and Jeff Mealy talking directly. So that's where this shortened line of communication on the bottom came in very handy. Of course, we still have all of the construction records. We still went through the entire submittal process officially for all of these, but just to foster communication and speed up the process, this proved to be very helpful. Okay, this is one of my favorite pieces. We got to go and talk to the school children in Logan. There is only one school in Logan, K through 12. And so we ended up doing two presentations, one for kindergarten through 5th and one for 6th through 12th. And we did get to keep them age appropriate, but we talked to them about the entire process. These kids had been watching this bridge being built for over a year at the time we talked to them. So Nyssa got to come, I got to come, and then also Mike Bold from Malcolm International, who is the engineer who built the bridge, was there. And we got to talk to them about how a segmental bridge is like Legos and rubber bands, and how balanced cantilever construction is like two children on a seesaw, and how the bridge type was selected because we had to protect the fish and the food chain. And I think one of my favorite parts of this was when we were talking to the kindergarten through 5th grade class, we really got into a discussion about loads, and they were really into it. And one of them suggested that we needed to design the bridge for bear attacks. So I think that you should all be looking for that in one of our future editions of the LRFD bridge design specifications from these really smart kids in Logan. But we also did make sure to talk to the 6th through 12th graders about STEM fields and construction trades, because we wanted them to know all of the different jobs that Mike Wold needed employees for, and all of the different engineering careers that they could go into that Nyssa and I are more familiar with. So I think we got great feedback from the school administration. I definitely had fun. I think you did too, Nyssa, and thank you definitely
for the highlight of the project.
Yeah, definitely. Oh, one thing I forgot to mention, Mike Wold with construction scheduling, he compared that to a football play where each different player has a role and they know what to do, but it all has to be happening at once. So I think that it went really well for the kids and for us. And I hope that they were able to take some of that back to their parents and tell them how that bridge project was going. Okay, so another really critical thing for us, NMDOT was having a little trouble at the district level being able to get approval for our inspectors to travel to the grouting training. And ASBI really stepped in and helped out here. They ended up coordinating to have Greg Hunsaker and Brian Merrill come out to the project site. And so we were able to get all of our inspectors, some of our Bridge Bureau engineers, and even one of the contractors personnel trained in the grouting before it began on the project. So this was really a huge thing for us to be able to get those guys trained when we seemed to be unable to get them cleared to actually travel to the training. So a special thanks, as it says on the slide, to Greg Freebie, Greg Hunziger, Brian Merrill, and Ingrid Ramsey for putting that training together, getting the site organized, shipping out the training materials. And it was a really great learning experience for me too. So a big thanks to you guys. Okay, here's what's coming next. We're going to complete the overlay. It's almost finished. They've just got to roll out the last few square yards of it and then groove it. And then we will probably be having a ribbon cutting, I think, with the villagers and some of our DOT leadership. And then, of course, we have to demolish the old bridge once we've moved traffic over. We have a couple things we got to pay close attention to. This bridge was tested for lead paint, and from what I recall, those who tested it said it has one of the highest levels of lead paint they've ever seen. And it's over an environmentally sensitive waterway. So we're going to have to be real careful, monitoring and containing as it comes down to make sure that we're protecting the wetlands and the river below. And then also we're concerned about safety because it's fairly high up in the air. And so we want to make sure that there's plenty of safety thoughts going in. I think that wraps it up, and we are certainly open to questions. Thank you, Nyssa, for all of your work on this presentation, and ASBI, Greg, for the opportunity to present on this bridge today.
Absolutely. Well, thank you, Nyssa and Kim. A great presentation. If you all want to turn on webcams now, we talked about sharing webcams so that you all could see who is answering questions. And I know Tim Berry said I don't think his webcam's working, but we're going to ask Tim Berry to moderate through the questions. We had a number of questions that came in during the session, and so Tim is going to serve as our moderator. One question that did come up that I will answer is somebody asked if the recording was going to be made available, and yes, it will. And then with the permission of the presenters, we'll also be putting up a PDF of the presentation. But you'll find those materials on the ASBI website where you registered for this webinar, and you'll also find the recordings from the past webinars. So if there's a webinar you missed, like the one on the JFK Causeway we did last month, you can go there and view that video at any time. It's available on demand. So with that, I'm going to turn it over to Tim.
Thank you, Greg. We'll get into the questions. I think obviously the first question has to be about bear attacks. That one was the top of my mind too. But we'll give you some time to think about that one. You had mentioned about the obviously the difficulty with personnel. Was that personnel availability in the discussion when choosing the type of bridge and going segmental? Was that part of the discussion?
Yeah, it was part of our structure selection process. We knew that it would be a challenge with the rural environment, but that this is also the first type for the state. So it was a challenge that we knew would have to be addressed by the contractor, that they would need to bring in some specialty staff for the construction. And then it was something that Malcolm really addressed on their side as far as training the workforce and helping to bring the local workers up to speed.
Okay, couple questions related more to the design and the construction. First of all, one quick question: were all the tendons internal, or were there some external tendons as well as part of it?
All the tendons for this one were internal. We had top slab longitudinal tendons and then bottom slab continuity tendons for the closures.
All right, thank you. Another question: we saw a bunch of pictures of the construction during the cantilever construction. Was there any measures used for stability of the cantilever during construction? Were there any temporary supports or counterweights or anything like that that were used?
There was not, and part of the reasoning, and you can see in that picture for the Q&A, part of the benefits of having those twin wall columns was that they were very efficient in handling our out of balance cantilever loads. We had originally taken a look at the design with a single column, and understanding that it would potentially, we would have to crack the column due to the significant moment from our full cantilever. But then we switched the design to the twin wall columns, and those took the large moment and effectively turned them into a couple that was handled more efficiently during the cantilever construction.
Okay, great.
Which was something we talked about with the kids at Logan. Kim had mentioned the seesaw, so we were talking to them about having a single pivot point versus a little bit more stability with two.
No, that's awesome. So I know you had mentioned about the issues with the tendon elongation that you encountered. Were you able to come up with a reason or a cause that was causing that?
We did do a couple of friction and a friction test along the way, and we adjusted our actual friction and wobble coefficients during construction. But then we were just finding that the longer tendons, we were having less elongation, and they were very close to our plus or minus 7% allowable limit. Obviously, if something was way off, we would address it. But if something was just a little bit off, that's where we came in with that flow chart to be able to effectively deal with it in the field. Okay.
Someone had asked about the concrete strengths of the concrete for the superstructure. Just what were they typically?
6,500 PSI was our concrete strength, and the contractor needed to get strength early on in order to be able to tension the segments. So we had a high strength concrete, and our final strengths were kind of even blowing our required out of the water. I think that they're getting ultimately like 10 KSI or so strength concrete.
Okay, we had a couple questions about the bearings, and I'll kind of summarize it into one. Number one, basically, what was the decision that drove what looked like the integral configuration, and were bearings considered over the piers? And then also, and sort of related to that, is this bridge in a seismic zone?
So the bridge is in a low seismic zone. It was something that we checked during design, but ultimately did not control our design because we were in such a low seismic area. And then for the kind of integral at the piers versus the bearing, we were able to kind of control our loads with the integral interface there, and it really minimized having extra bearings or extra maintenance that comes with those bearings, and kind of keep the design more simple for the cantilever area.
Okay. Couple other real quick ones. Someone had asked about empty ducts. I think you had mentioned that there were basically future tendon ducts that were incorporated into the construction of it.
Yeah, we had the capacity for additional tendons with our design ducts that we had, but we also have provisional ducts in our structure as well. So these could be used down the road if for maintenance purposes additional strength is needed, or if additional if there was deflections that needed to be addressed, or higher loads down the line that the structure needs to be able to carry. We do have those provisional ducts in there for future capacity.
One more quick one. I think I know the answer, but I'll go ahead and ask it anyway. Someone asked, were the segments cast in one placement?
Yes, it was. So our pier table, those were cast in multiple lifts, but the segments themselves were cast all together. Yes, they were. Well, they cast up the side with like a thicker slump in order to get that so that they wouldn't kind of blow out at the bottom of the web wall, and then beyond that they cast the rest of the segment. So yeah, we didn't have a joint.
Okay. Yeah. Okay.
Yeah.
A couple more just popped in. Let me see real quick. So someone asked about, again, given the challenges that you talked about delivering concrete, was precast ever considered? Precast segmental versus cast in
Yeah,
place?
and that's a really good question. Precast is something that we considered during the structure selection process. This bridge, for the size of it, for segmental, is kind of a smaller segmental bridge. Precast becomes a lot more cost effective when you have a lot of repetitive precast segments that are being cast, and you can just be very efficient with kicking out those precast segments. So cast in place kind of inched ahead here based off of the overall size of the structure for cost efficiency compared to setting up an entire precast plant and doing it with precast.
Okay, a couple more here real quick. Someone actually, this is an interesting question about, was the bridge considered significant under the National Historic Registry, the existing bridge? Was there any issues with that?
Yeah, so it is considered historic, and we went through an entire historic documentation process during preliminary and final design. So I'm familiar with this. It's not my specialty to know all the different nomenclature with it, but they did we had parametrics as part of our design team, and they did a historical documentation, a full report and record of the history of the corridor and the project. There's also an adjacent railroad bridge in the area as well. They created a historical pamphlet on the structure, and so there was a process of even though they're demoing the existing bridge, there was a process of going through the historical requirements to document everything that had been done with the bridge in the corridor to date.
And if I could just
Okay.
add, we do have a similar box truss south on I-25 towards the south end of the state. So that allowed us to be able to demo this one.
Okay. One more, Greg, I think then we'll probably need to wrap it up. Someone asked, is there any mass concrete elements of the project, in particular the diaphragms, or were there any mass concrete elements in the whole bridge?
No, we have a full diaphragm at the center. If there's an access, there's access through the diaphragm that we have there, but the entire bridge besides that is a hollow structure. If that answers the question.
Greg, I think that pretty much wraps it up. There may be a couple other questions that we probably don't have time to get to that maybe we might be able to answer at a later time.
Yeah, what I'll do is we will capture those questions here, and I will send them to our presenter and get answers provided, and then we'll email those out to the attendees and also post them up on our website. So Thank you everybody for attending today. Again, give it about a week to get your professional development hour certificate. So if you don't hear from us by next Wednesday, you can certainly drop us an email at the email address you see on screen. And again, a little reminder to follow us on LinkedIn. You'll see a lot of kind of not just updates on upcoming ASBI events, but also we're kind of digging through the archives and looking back on some of our past projects and award winners and just kind of interesting segmental projects across the country. So with that, again, thank you, Kim and Nyssa. Appreciate your time today. Always enjoy your presentations on this structure and look forward to more presentations for New Mexico DOT on other segmental bridges. So with that, we will close the webinar. And again, thank you, everybody.
Thank you. Thanks, Greg.
Thank you.